Alright, we're going to take properties and equation notes today. Each step in the solution of the equation will be justified using the field properties of real numbers and the properties of equality. These properties may be modeled using manipulatives and pictorial representations. Again, if you need to pause the video as we go, do so. First set, properties of equality. Reflexive property of equality is A equals A. Symmetric, if A equals B, then B equals A. Transitive, if A equals B and B equals C, then A equals the C. Substitution would be when we solve it, x equals 2 minus 3, then x equals negative 1. Okay, so you're looking for a change. So it's pretty much we solved this part here. Try that again. This part became this part here on the other line. So that's the substitution part there. Addition property of equality. That is where we add the same thing to both sides. I've underlined it. So that's the change you're looking for. When you see the original equation plus 3 to both sides of the equals, you've got a new part there. So that's the addition property of equality. Subtraction property of equality is the same thing, where 2x plus 3 equals 5, then 2x plus 3 minus 3 equals 5 minus 3. Multiplication property, x divided by 4 equals 5, then 4 times x divided by 4 equals 4 times 5, where we multiply both 4 times each thing. Division, 2x equals negative 12, then 2x, we would divide that by 2, equals 12, negative 12 divided by 2. And of course, it stays right there. Field properties of real numbers. Closure means that if you do math on real numbers, the result will be a real number. This has closure. Commutative property of addition is a plus b equals b plus a. It's the same for multiplication. So if this was a times instead of this was a dot here and a dot here, it's the same property. Associative, a plus parentheses b plus c equals a plus b plus c. Same for multiplication. So if those pluses were dots, it would be the same property. Inverse of addition is the first one, this one here. Negative a plus a equals 0, always equals 0 for inverse of addition. And then a times 1 over a is equal to 1. That's the multiplication inverse property. Identity property, a plus 0 equals a, or, and that was for addition, and then a times 1 equals a, again, identity. You do math and you get the same thing. And of course, distributive property, a times parentheses b minus c, multiply both of the terms inside the parentheses, all terms inside the parentheses, with the a. Here's an example problem. We start out with step 1. Step 1 is given. So that means that this is the original. So this and this is given right here. So we start out with the given one. Then what you're doing is you're looking in between these two. What happens from here to here? And so we notice the change is plus 6 and a plus 6. So that is the addition property of equality. Again, what is the change from 2 to 3? We see that they did this part right here. The negative 6 plus 6 is a 0. So this right here was our inverse property. Okay? So again, this right here is where we focus in. That's the only thing that's different. So that is the additive inverse. Okay? Next one, step 3 to 4. We did the 0 plus something equals this. So that is the additive identity property. So what we see changes from the step 3 to step 4 is that there. As we go down the line here, the next step from 4 to 5 is they just simplified some stuff, and that's called substitution. So right here, this became this, all on the right side, that's substitution. Okay. Multiplication property equality is what happens next. So again, when you look, you see the 3 halves times 3 halves. That happens to both sides of the equal. So that's called the multiplication property equality. Then, when we go from 6 to 7, we see that this became 1 right here. And so that's what changes. The x stays there, the 3 halves, and that changes as well. That's called the multiplication inverse. But if you notice, something else changes in that problem. So notice we wrote the property only for the multiplication inverse of this one, but actually it has two things going on here. It would be that and this other one here over here. This got simplified a little bit. So we could also say it's substitution in red there. So both sides change. They only wrote the multiplication inverse, but it could also be substitution. The next step from 7 to 8 is this here. All right. So from 7 to 8, what changes is this side over here on the right. 1x times x, that's the identity. And then what changes from here to here is just the answer, which is substitution. Now for some more vocabulary. A solution to an equation is the value or the set of values called the solution set that can be substituted to make the equation true. So for instance, if we had x squared equals 25, the solution set or the answers to this would be 5 and negative 5, because 5 times 5 is 25, and negative 5 times negative 5 is also 25. So the solution to this has 2, and we can put it in a set with the brackets. So we use brackets to show a solution set. Some more vocabulary. Set builder notation is used to represent solutions. For example, if the solution is y equals 10, then in set notation, the answer is written like this. All right, so there's two types. There's this one here where you say y colon y equals 10, or we can say y slash y equals 10. Again, all they did was replace the colons with the slash there. So for instance, if we said we want to solve this solution when x equals 5, we would put 5 in, 2, 5, plus 5. Okay, so the solution set here would be 10 plus 5, and so y equals 10. So our solution set would be written like this. Again, that's the example for y equals 10. If the solution set has no elements, there's no answer for it, the solution is called the empty set or the null set. And the set notation is this circle with a line through it, or it's empty brackets, nothing's inside it. So for instance, this is an example of something that would give us a empty set or no solution kind of situation. Okay, so if we try to solve this, we could try to solve this like this here. We would say negative x minus x. This goes away. So 5 equals 0. That is not true. So the answer to this would be the empty set or no solution. An element or a member of a set is any one of the distinct objects that make up that set. For instance, if this was my set, there's 6 numbers in this set here. I could say an element of this set, one of the elements is 5. Another element is 4. So those are all elements of the set. Sometimes, instead of just putting single numbers, we might say that it's the whole numbers. So what's an element of the whole numbers? So you would just give an answer for the whole numbers. You could say 0. Actually, this is the whole numbers, some of the whole numbers anyway. So that's what we would do for those. So those are called elements. The coefficient is the numerical part of a term. A constant is a symbol representing a value that does not change. So again, if we said the coefficient, these are coefficients, the 3 and the 4. There is a numerical part of the term. And a constant is just a number that does not change. So this number does not change. So 3 and 4 is the numerical part. It's 3 times the x and 4 times the y. So they might change depending on what x and y is, but the 7 will not change. It's always going to be plus 7. So that's the difference between those two things. Types of solutions. There are 3 types of solutions, really. By transforming given linear equations into simpler forms, the number of solutions can be determined. An example of a linear equation with one solution is this here. So if we were to solve this real quick, we would say minus x, and we could combine a step here and say plus 2, plus 2. So I would do this. That's 5x. That goes away. That's 5. And divide by 5. Divide by 5. And x would equal 1. 1, not the 3. So x equals 1. If we wanted to check that, we would do 6 times 1 minus 2 equals 1 plus 3. So if we look here, that's 6 minus 2, which is 4. And this is 1 plus 3, which is 4. So 4 equals 4. That's how we check. We put it back into the original equation. An example of a linear equation with no solutions is this here. We've already looked at one, but we would say minus 2x minus 2x. That's 0 equals 1. That's not true, so it's no solution. Or we might write the empty set or the bracket empty set. Okay, so those are all possible solutions for that there. And the last one here is an example of a linear equation with infinite number of solutions, meaning they're all real numbers. So we got 5x plus 10 minus 2x, 5x plus 10 minus 2x equals 3x plus 10. So if you solve this, you can get possibly 3 different answers. You could get x equals x, 10 equals 10, or 0 equals 0. All 3 of these here are considered true. X always equals x, 10 always equals 10, and 0 always equals 0. So whenever you get those situations, we are looking at things that has an infinite number of solutions, which means all real numbers will work for these situations. So we could solve some of this here. We'd get 3x plus 10 equals 3x plus 10. So if I started with the x, the variable on both sides, which is how I taught it, we would subtract 3x and 3x, and we get 10 equals 10. And once you get a true statement like that, you're done. You might also continue on. Well, I'm going to take 10 away from both sides, and we get 0 equals 0. Okay, so that's how we could show that when that case happens, it's this here. So you're going to either get an x equals something, you're going to get something that doesn't make any sense for no solution, and you're going to get something that makes perfect sense. And when that happens, it's all solutions. So there's 3 types there. And for your math joke of the day, what do you get if you cross a math teacher and a clock? Arithmetics. Get it? Ha ha.